We all want a greener, more efficient power grid, right? I mean, of course we do. But what if the price for all that efficiency was your privacy? What if the smart grid knew when you woke up, when you left for work, even when you're on vacation? Well, today we're going to break down a really cool new framework that shows how we can share power without sharing our private lives.
So let's just start with a simple question. If you have solar panels on your roof, you probably feel like you're doing your part for the planet. And you are. But here's the thing. There's a really good chance you're generating a ton of power when you don't actually need it. And that extra energy? It might just be going to waste.
And this brings us to the star of our show today, the prosumer. It's a bit of a buzzword, I know, but all it means is someone who both produces and consumes their own energy. And as we're about to see, being a prosumer in today's world comes with a pretty unique and very modern dilemma. Okay, so you gotta picture the modern energy grid as having three key players. First, you got the prosumers, all the homes with solar panels. Then there's the big central utility grid that we're all used to. But it's this third piece that's the real game changer. Shared community resources, like a big neighborhood-sized battery. And that is where things start to get really interesting.
So the first big problem is what the research calls a temporal imbalance. That's actually really simple. Your solar panels are cranking out power around noon when the sun is high and you're probably at work. But the real energy rush hour, that's in the evening when everyone gets home, starts cooking, turns on the lights, and the sun is long gone. It's a classic mismatch of timing.
Then you've got the second problem, a spatial imbalance. It's all about location, location, location. So you might have all this extra solar power at 2 in the afternoon while your neighbor right next door is plugging in their electric car and could really use that energy, like right now. The power's there, it's just not in the right place at the right time.
So how do we fix all this? Well, the first step is to go after that timing problem. If you can't use the energy the second it's made, you've got to have a way to save it for later, right?
And the proposed solution here is a pretty clever idea called capacity renting. I mean, let's be honest, buying a giant battery for your house is crazy expensive. But what if? What if you could just rent a small slice of a much bigger shared community battery? You'd get all the storage you need, but without that massive price tag.
Okay, so shared batteries help solve the when problem. But that still leaves us with the where problem, all that energy that's just in the wrong spot. The next piece of this puzzle tackles that head-on by connecting neighbors.
The answer is peer-to-peer energy trading. Think of it like a tiny, local energy market, just for your neighborhood. Instead of selling your extra solar power back to the big utility company for pennies, you can sell it directly to your neighbor with the EV for a much better price. It's just way more efficient for everybody involved.
So now we've got two great solutions on the table, shared batteries and neighbor-to-neighbor trading. The next big challenge is, how do you make them work together? How do you create a system that's smart, automatic, and actually benefits everyone?
And this is where the complexity just explodes. I mean, for one home, you could maybe figure it out. But for a whole community of thousands of homes, the system has to decide every single minute of every day what the absolute best option is for everybody all at once. It's a massive optimization puzzle. So this framework proposes a really clear order of operations, kind of like a pecking order for your power. First, you lock in your spot in that community battery. Then you see if you can trade with your neighbors. Whatever power is left over after that, it goes into your rented storage space. And only as a last resort, do you bother dealing with the big utility grid.
So how in the world does this system find this perfect balance for everyone? Well, it models the whole community like a game, where every single home is trying to get the lowest possible energy bill. The algorithm's one and only goal is to find what's called the Nash equilibrium, that perfect sweet spot where nobody can improve their situation by changing what they're doing. It finds the best, fairest outcome for the entire group.
But this perfectly tuned, data-hungry system has a bit of a dark side. To make all these amazing decisions, it needs to know a ton about everyone's energy habits. And that, right there, is where we hit the privacy puzzle.
This quote from the source paper really gets to the heart of it. Even if you're not handing over your data directly, these super smart algorithms can analyze the patterns of communication back and forth and start to figure out your personal habits, like when your house is empty. Yikes.
And this really is the billion-dollar question, isn't it? We all want the savings and the efficiency of a smart grid, but we can't just give up our fundamental right to privacy to get there. So how do you build a system that knows everything it needs to know to work without actually knowing anything personal at all?
The solution is this brilliant piece of cryptography that sounds like something out of a spy movie. It's called homomorphic encryption. The easiest way to think about it is like this. Imagine a locked box. You put your private energy data inside this box, lock it, and give it to the system. The system can then do all the math it needs to do on the locked box without ever being able to see what's inside. When it's done, it gives you back the box, and out comes the perfect energy plan for the whole community. And your private data was never, ever exposed. It's amazing.
Okay, so the theory is fantastic. It's smart, it's efficient, it's private, but does it actually work in the real world? Let's take a look at the results from their case study.
The numbers here really do speak for themselves. In the baseline case, the old way, where people could only deal with the main grid, the community's total daily energy cost was just under 7,100 CNY. But then, in case 4, with both the battery renting and the neighbor-to-neighbor trading turned on, that cost dropped to under 6,600 CNY. That's a huge difference.
And visually, the impact is just so much clearer. You look at this bar chart, and you can see that significant drop in cost. We're not talking about a small tweak here. This is a substantial savings for the entire community.
The final takeaway really boils down to this one powerful number: a 7% reduction in daily energy costs for the whole community. This shows that you can have a grid that's smarter, cheaper, and greener, all while making sure that everyone's privacy is protected.
And that leaves us with one final thought. This framework isn't science fiction. The tech, the models, they exist today. So the real question isn't if we can build a smart grid that respects our privacy, but just how quickly we can make it a reality for your neighborhood and for neighborhoods everywhere.